Imagine holding something so valuable that even the richest person on Earth could never buy it. Not because they lack money, because there simply is not enough of it to purchase. It is not gold. It is not diamonds. It is not plutonium. It is not the rarest gemstone ever discovered. It is something humanity has created, but can barely keep alive. 1 gram of this substance would be worth more than $60 trillion, more valuable than fleets of aircraft carriers, more valuable than entire national economies. Yet almost nobody has ever seen it. Scientists have spent decades trying to create it. They celebrate every successful experiment, only to watch it disappear almost instantly. Its name is antimatter. Everything around you is made of matter. Every mountain, every ocean, every planet, every star, every person who has ever lived. But nature also created a perfect opposite. An identical twin with one crucial difference. Its electric charge is reversed. When matter and antimatter meet, they annihilate each other. Every particle disappears. Nothing is left behind except pure energy. This is not science fiction. It is one of the most extraordinary predictions ever confirmed by physics. Hidden inside Einstein's famous equation, E=mc2, is the explanation for why antimatter stores an unbelievable amount of energy. But the greatest mystery is not its price. It is its existence. The Big Bang should have created equal amounts of matter and antimatter. If that happened, why does our universe still exist? Where did all the antimatter go? To begin answering that question, we must travel beneath the border of Switzerland and France. Hidden underground lies one of humanity's greatest scientific achievements, a machine built to recreate the first moments after the birth of the universe. Welcome to CERN. What is antimatter? Scientists did not discover antimatter by accident. Its existence was first predicted with mathematics. In 1928, physicist Paul Dirac found something strange hidden inside his equations. They suggested that every particle in nature should have an opposite twin. At first, the idea sounded impossible. Then the impossible appeared. In 1932, the positron was discovered. It became the first confirmed particle of antimatter. Since then, scientists have found antimatter versions of many familiar particles. An electron has a positron. A proton has an antiproton. A neutron has an antineutron. When combined, they can form anti-atoms. They look almost identical to ordinary atoms. But one tiny difference changes everything. Their electric charges are reversed. That single difference makes antimatter one of the strangest substances in existence. It can never peacefully mix with ordinary matter. The instant they touch, both disappear. Their mass is converted into energy with extraordinary efficiency. This is not an explosion caused by fuel. It is matter itself becoming energy. So where can scientists find antimatter today? Not in mines, not in oceans, not on mountaintops. They have to create it. And for that, they need one of the largest machines ever built. Deep beneath Europe, inside CERN, particles are accelerated to nearly the speed of light. They collide with unimaginable force. For the briefest fraction of a second, conditions resemble those just after the Big Bang. Out of those collisions, tiny amounts of antimatter are born. Capturing them is even harder than creating them. Because the moment antimatter touches the wall of its container, it vanishes. So scientists use powerful magnetic fields to suspend it in empty space. Even then, they can only keep a few particles alive for a limited time. Every experiment is a race against disappearance. And every particle they save teaches us something new about the universe. In the next chapter, we'll see why producing even a microscopic amount costs more than almost anything humanity has ever made. Why is antimatter so expensive? Now comes the question almost everyone asks. Why would 1 gram of antimatter cost more than $60 trillion? The answer begins with energy. Creating antimatter is not like manufacturing steel or refining gold. It starts by accelerating ordinary particles to incredible speeds. Those particles are pushed around a circular tunnel stretching for kilometers. They travel at almost the speed of light. When they collide, enormous amounts of energy are released. For a tiny fraction of a second, new particles appear. Among them are a few particles of antimatter. But producing them is astonishingly inefficient. Billions of collisions may produce only a handful of useful antiparticles. Most disappear before scientists can even detect them. The survivors must immediately be trapped. That requires powerful superconducting magnets. Those magnets must operate at temperatures colder than deep space. The entire facility consumes vast amounts of electricity. Thousands of scientists maintain the instruments. Years of engineering support every experiment. And after all of that effort, only an unimaginably tiny amount of antimatter is collected. If you gathered every particle humanity has ever created, it still would not equal a single grain of sand. In fact, humanity has never come close to producing 1 gram. At today's technology, creating that much would take an extraordinary amount of time and energy. That is why estimates reach tens of trillions of dollars per gram, but price alone is misleading. You cannot order antimatter online. You cannot store it in a safe. You cannot carry it in your pocket. Even if someone offered unlimited money, there is almost nothing available to buy. Antimatter is valuable because it is unbelievably difficult to create and even harder to keep alive. And yet scientists continue trying. Because what they learn may change our understanding of the universe forever. In the next chapter, we will see what happens when antimatter finally meets ordinary matter. Antimatter is the most expensive substance on Earth. A single gram would cost roughly $62.5 trillion. But it's not just its price that's extraordinary, it's the physics behind it. Imagine releasing a single particle of antimatter into an ordinary room. It would survive for only an instant. The moment it touched the air, it would disappear. So would the particle of ordinary matter it collided with. This process is called annihilation. Neither particle survives. Instead, nearly all of their mass becomes pure energy. No chemical fuel is burned. The particles themselves become energy. This is one of the most efficient energy conversions known to physics. Fortunately, scientists work with unimaginably small quantities. There is never enough antimatter in a laboratory to create a catastrophic event. But the physics is extraordinary. If 1 gram of antimatter could meet 1 gram of matter, the energy released would be enormous. That idea has inspired countless science fiction stories. Reality is very different. The hardest part is not using antimatter. It is creating it. And an even greater challenge is storing it. A normal container cannot hold antimatter. Glass cannot. Steel cannot. The instant antimatter touched the container, it would vanish. So scientists suspend it inside magnetic fields in an ultra-high vacuum. The particles never physically touch the walls. It is like balancing invisible dust inside a magnetic cage. If the trap fails, the antimatter disappears immediately, not because it escaped, but because it touched ordinary matter. This extraordinary behavior makes antimatter one of the most difficult substances ever studied. And yet scientists continue their work. Because its greatest value may not be energy, it may be the key to understanding why the universe exists at all. Why do scientists keep making antimatter? If antimatter is so expensive, why keep creating it? The answer has very little to do with weapons. In reality, antimatter is already helping save lives. Every day, hospitals around the world use technology based on antimatter. PET scanners rely on positrons to produce detailed images inside the human body. Doctors use those images to detect diseases much earlier than before. Cancer is one of the biggest examples. Without antimatter, many diagnoses would become far more difficult. But medicine is only the beginning. Physicists are asking much bigger questions. Why does the universe exist? Why is there far more matter than antimatter? If both were created during the Big Bang, where did the missing antimatter go? Every experiment at CERN moves scientists one small step closer to an answer. Researchers compare matter and antimatter with incredible precision. They search for even the smallest difference. A tiny mismatch could rewrite our understanding of physics. Antimatter also inspires future space exploration. Some engineers believe it could one day power spacecraft. Because antimatter contains enormous energy in a tiny amount. Today's technology is nowhere near that goal. But scientists continue studying the possibility. Every discovery expands our knowledge. Sometimes the greatest inventions begin as impossible dreams. Electricity once seemed impossible. Flying across oceans once seemed impossible. Walking on the moon once seemed impossible. Antimatter may become another chapter in that story. And perhaps its greatest discovery has not been made yet. In the final chapter, we explore the biggest mystery of all, the greatest mystery of the universe. For decades, scientists believed they understood the beginning of the universe. Then one simple question changed everything. Where did all the antimatter go? According to our best theories, the Big Bang should have created equal amounts of matter and antimatter. If that happened, neither should have survived. Every particle of matter should have met its opposite. The universe should have become nothing more than pure energy. Stars would never have formed. Galaxies would never have existed. Planets would never have appeared. Life would never have begun. And you would not be here watching this video. Yet somehow matter won. Somewhere in the first moments of cosmic history, something changed. The balance was broken. For every billion particles of antimatter, there were just slightly more particles of matter. That tiny difference changed everything. After billions of annihilations, only a small amount of matter remained. That tiny remainder became every galaxy, every star, every planet, and every living thing. Scientists still don't know why this happened. It is one of the greatest unsolved mysteries in modern physics. Experiments around the world continue searching for the answer. CERN is one of the most important places in that search. Every collision may reveal a clue. Every new measurement could rewrite physics. The answer may transform our understanding of the universe forever. And perhaps one day it will explain why anything exists at all. In our final chapter, we ask one last question. What could antimatter mean for humanity's future? Antimatter is the most expensive substance on Earth, costing an estimated $62.5 trillion per gram. It's created in places like CERN, using massive particle accelerators to smash atoms together at near light speed. But keeping it alive is the real challenge. Since it annihilates upon contact with regular matter, scientists must suspend it in vacuum-sealed magnetic traps just to stop it from vanishing in a flash of pure energy. Humanity has only taken its first steps into the world of antimatter. Every experiment opens another question. Every answer reveals another mystery. Today, antimatter exists only in microscopic quantities, but tomorrow's discoveries may change that. Some scientists imagine spacecraft powered by antimatter engines. Others believe it could unlock entirely new areas of physics. Perhaps it will never become an everyday technology. Perhaps it was never meant to. Its greatest value may be knowledge itself. Understanding antimatter means understanding the birth of the universe. It means understanding why galaxies exist, why stars shine, why planets formed, and ultimately why we exist. The most expensive substance on Earth is not valuable because someone can sell it. It is valuable because every particle carries information from the first moments after the Big Bang. That makes antimatter more than a scientific curiosity. It is a time capsule from the beginning of everything, and somewhere inside its secrets may be the answer to one of humanity's oldest questions. Why is there something instead of nothing? Until that answer is found, scientists will continue searching. Deep underground, inside powerful laboratories, one collision at a time. One particle at a time, one discovery at a time. The universe still holds countless secrets. Antimatter is one of the greatest. And this story is only just beginning. Because beyond every discovery, there is always another mystery waiting to be found.